My name is Stefany, and I am the creator designer of the C256. Well, actually, it's getting bigger and bigger now. New retro computers lines of products. Um, I don't think I'm going to talk much about the philosophy behind the new retro computer thing. I would suggest that you come back tomorrow, and I'll talk more about it. What I got myself in that kind of weird place where I'm designing something that is not compatible with anything. And it's not meant to be compatible with anything, but it's really a tool to get people back to a place where when we, back in the days when we did retro computers, we were after these, back in the 80s, we had all these new retro computers. And I think one of the thrill of back in the day, the nostalgia that we have today is one of those aspects was to actually discover the machine. So in a nutshell, that's basically what those new, when I call a new retro computer like the Mega 65 or the ever maybe will come one day, the X16, is really meant to get people back into that state of discovering something new that we don't know. So today, what I'm going to talk about is really the graphic engine that I've been developing over the last 4 years, because it's actually, I started 4 years ago. About the anniversary is the 18th of April 2018, so we're like four years in. And it all started with David Murray and his request for new retro computers. And again, I'm not going to talk about that stuff because I've talked about it many times before. So today I want to really focus, because it's a technical presentation, on the inner workings of VICKY 2. So the first generation, the first computer I designed, it was VICKY. It was a 16-bit bus, and I migrated to a 32-bit bus to get more bandwidth. And since then, I've been developing it more and more. And now I moved from not necessarily completely, but I've been moving away from the 8-bit, old 8-bit CPUs, because it's like there's a lot of people there already. So I decided to go and move towards more the 32-bit. So eventually there'll be a VICKY 3 version of this, which will be 2 different buffers and more capacity, more capabilities. But anyway, I'm digressing a little bit, but basically the introduction of what I'm going to present today is really about the inner workings. And I cannot go very deeply into it because it becomes very complex very quickly. But I'll try to explain basically the different blocks within the chip and what it does. And it's an FPGA development and everything. It's a custom thing that I designed, and it's private. It's not open source. The reason for that is mainly because of software compatibility and make sure that everybody works on the same chip. It's basically, the way I see it is that the way I presented it in the past was really, the FPGA for me is meant to be like an ASIC, something that was set in stone, nobody could change it. And so making it open source where everybody could change it would make it like, it doesn't make any sense to me, or it didn't make any sense to me back in the day. It still doesn't make much sense. Although if I was going to quit the world of new retro computers, I would probably release it. But it's really about having consistencies for people to develop on something that is always the same thing. Anyway, so the agenda today is, well, I guess I have a little bit more room. I hope so. I can go through my agenda today without being pushed out. I'll do a little bit of introduction. I'll go a little bit deeper on my background that I usually skip over really quickly. Assumption of level of knowledge. Last year, we did something a little bit deeper in Verilog developing, although we didn't do a lot because, 40 minutes, it's not a lot of time, but it was definitely more hands-on. This year, not as much. And I'll go through the different portion, like I said, about the chip, what it does. I wanted to show you as well. I think I showed it a little bit earlier. This is like a board. This is the A2560U. It's a 68,000 base board. And so you basically have the FPGA, and I'm going to talk soon about the video DAC, which is here, and the memory buffer, that's VRAM that is here. So physically, that's something that we're using and exists. And this is the A2560 Phoenix U, which is the user version, the small version. So there's way more. So I suggest that you go on the website. And then I don't want to waste too much time on this, so I'll move on. right away. So I come, I'm a Gen X. I was born in 69. My father brought this C64 in 1982, but it was the first year it was released. We didn't do much with it. That was my introduction to computers in general. Took a couple of years to get into it, and I started having fun with it. I started doing some hacking, game hacking and stuff like this. So I started fiddling with hardware. I also at 13 started doing, using my brother's kit, Radio Shack kit for those who remembers that, plugging. And I got very interested into this, and I started doing a lot of, hacking on my own. I was always been a very on my own person, doing my own thing. When people were going out and having a drink, I was doing electronics. So that was a very big passion from very early on. And I started my career as a technician. I never been to university, so I don't have a bachelor degree, but I'm a little bit like Elon Musk. I learned, and all these big, guys that just were school dropouts, learn on the heap. And that's how basically I went through my career, just learn a lot of stuff on my own, and, struggle, get myself in trouble, and usually go for the harder path. But there's always a reward by doing this. You learn something and you get better. So I started being a technician, but within maybe half a year, I ended up being in the engineering department, and maybe a few months later, I was responsible for my own project development. So I was definitely early on definitely had a lot of skills into product development in general. I tried to develop, started companies, like the first one was 96, doing some acceleration for the geometry processing. And you have to remember, this is the time where, the first rendering chips were coming out, the rendition chip, the NVIDIA chips, which was shipped at the time. There was AMD, not AMD, but ATI, all these guys were there. They were all starting and then fighting with each other. The same thing, relationship with the different retro computers, or back then the home computers. A lot of choices and a lot of possibilities. And then over time, it just got integrated and everybody bought each other. And then NVIDIA came on top and with ATI. So that one failed, but that was basically a DSP trying to drive a rasterizer chip. So to complete the whole, processing flow of the 3D engine. And then I moved on. That company went bankrupt. I bought the bankruptcy back, but it was already too late. I failed miserably the second time as well. And then I went in sales, and then I didn't work out. I loved helping people, but I sucked at the politics of it, and there was a lot of it. And then I moved on into doing working for many companies to develop products, and got more skills, got more experience, and finally in 2004, not like it was like at that point, I started a company again, but I definitely lasted longer, but I didn't produce as much as I wish I would. It was because I was in Montreal, and then I moved in LA because I was really focusing on image processing. I always had this interest into graphics and pixels and stuff. I mean, for me, it's always been very exciting. I always say that there's so much potential in the pixel, way more than a packet of Ethernet, right? So the data transfer, because in the electronic industry, there's many different areas where engineers find their places. For me, it was always imagery, 3D graphics, and stuff like this. So, and processing of said pixels. So in 2004, I was focusing on trying to accelerate the image processing for for movie industry, like a black box that could make things process go faster when you do post-processing. But that was a time where, Intel processors were preferred because they were easy. Somebody came with a solution like this in the past, and, everybody they got stuck with a black box that could not be expanded. So the deal was, I came later, and then they didn't want to get involved, and software people were flaky, and, a lot of whoring around and pimps and whores to get your stuff accepted and everything. And since I'm not much of a political type person, I was like, okay, let's forget about this. And then 2008 happened. I moved to LA in 2008. So I was going to design this super parallel solution with mini processor. It was insane. But the parts I was going to use, the name of the company was Embrick. They went belly up like 2 months after I came in because of the crash in 2008, which I was not aware of at all. So then I kind of crashed a little bit. It was kind of hard. And then I got some money back from the R&D from Canada and everything. And then I started making and designing, global shutter cameras, digital cameras, which was very new at the time. And, but again, I'm not political, but I'm not a salesperson as much as I would like. I'm kind of too honest. So it's difficult to get me out of my own way. So eventually I kind of, I got the camera to a state, it was working and everything. And then I sold the design to somebody else. I worked for that person. And then in 2013, he ran out of money as well. And then I came back in 2013 to start working for other people again. And eventually in 2018, after working for different companies, I on the side, and David's, stuff was, it would be great if somebody would design something like this and like a retro computer with my, wish list. And eventually I got into it. I was amongst the very few who actually got in there, but I was in the mood for retro like a lot of people. And I did something, although I did it with my own money and I did it with my own angle. My own vision of what he wanted. And I started with the 816 and I created the first C256 Phoenix. And then I moved on from there and I started developing this graphic engine. So ultimately, like I wrote, the moral of the story is that there's really I've learned a ton with all those failures because it's mostly when I was in LA that I've learned to do FPGA, mechanical design, because I was on my own. So I got to hone those skills and learn, and I was always very good about the visionary aspect of developing a product. I had like a clear vision of what I wanted, but now that I was doing everything, then it just gave me a better edge. The other side of that is that ultimately when you're knowing how to do everything, you don't know how to do everything as deep as if somebody is doing a sole work, right? So I'm not as good as a pro that does only FPGA, for example. I'm just really good enough to pull it out and make it work. But otherwise, I'm sure most people would do what I'm doing way better if we segmented everything I'm doing in the product design. So basically don't be scared of failing, just do it and you learn a lot. And it's great. So today I basically got involved, and after that, the whole story after that is really the fact that I started as a hobby and I came to work in Vancouver for a digital camera company. And then I was just working and doing this on the side. And when I left the company or I was let go, in 2020, I was kind of resisting to go further with this. And I was like, okay, but I didn't feel like going back to corporate. The last job was really hard on me. I invested a lot of my energy and love in this, and it didn't turn out great. So after a few months and a failed attempt to go work in US in April 2000, last year, actually, I came back and said, okay, let's do it full time. And I've been doing it full time since then. And again, if you want to come back tomorrow or see the video tomorrow, I'll talk about the Gen X, which is really the ultimate new retro computers. And so that's what I'm doing now. And it's ultimately the thing I didn't want to do, because after the last time I started the company, I said, when I don't want to do that anymore. It's too much problems, too much. And then the universe has a way to bring it back on your lap when you don't want it anymore. Which basically means when you want something too much, it's like, no, you don't do it. You just let it go, and then it comes back, and then it's more organic. It just happens. You just have to go through with the flow. Anyway, moving on. At this point, there's no really prerequisite. If you have any knowledge of 3D graphics or a little bit how a video card works, it's great. I think it's meaningful. That's why I didn't want to go too deep, because there's many sections and everything. I'll try to explain as much as I can. It's really how you see it in your head, how the processing is being done. But otherwise, it's not like last year. Like I said, it's like you don't need like a Verilog background or anything. So being technically savvy is probably good enough. So no special prerequisite this year. So before we go any further, I want to make sure that everybody's on the same page. Something else I said last year was like, there's different ways to see things. There's different ways to do things. Since I didn't go to school, I was not like squared and schooled in a way to think a certain way, because I believe people going to universities usually learn more about how to process information more than what they need to learn. In terms of technical learning, it's more about how to go about learning stuff or to process information. So since I didn't go there, so I'm a little bit all over the place. So this is the representation of how a display is working. So basically the information you send out to the LCD screen or CRTs is usually, you'll have the VSync signals, you'll have the HSync signal, you'll have some blinking signal to say when on and off the ray gone. If we go back to we go back in time. So this is kind of a common knowledge. I mean, people kind of know that. Technical people know that. So I don't want to spend too much time on that, but just to the way I'm showing it, because if you look on Google, if you look for information about how the timing and display information is being displayed on screen, you're going to see very often that the blanking is on the right side and the V blanking is at the bottom instead of being on top. I don't know why, but I've always pictured the V blanking and the H blanking on the top left as opposed to be on the bottom right. But in the end, it doesn't really matter because the display doesn't care. You're just going to put your data, as long as the VSync and HSync and blinkings are at the right time, relatively to everything else, it's going to work. So I wanted to present it the way I see it, so it's easier to go along. I have put a small link at the bottom here because this is where you can find really resourceful timing information. It's kind of rare and difficult to find sometimes to know exactly at what clock cycles things happen. And this is really nice. The person who came up with this was really right on. So this is how I see so there's definitely a time where there's nothing happen on display, and it's going to be important later for how you manage the timing, the time to fetch the data off and on the VRAM and so on and so forth. And yeah, so I don't think there's anything else to say, but because we'll ultimately come back to it. So before I go within the VICKY2 core, there's two parts that are usually important, of course, to display an image. Most people nowadays, if they want to do a VGA, they usually use a R2R DAC with resistors with a VGA using an analog way of doing things. The VGA, I find the VGA to be it's in terms of color and everything, it's kind of nice when you have a CRT. But when you leave the CRT world and you go into the LCD, I think an HDMI or a DVI is definitely better. Send your data digitally is definitely better. So I try to stick with this. So you need a video DAC, but in reality, it's more a video DAC. In our case, the parts I use is doing both. So there's DACs to have a VGA output, but it's very finicky. It's very difficult to have a very clear image without having overshadow and stuff. It's very, very finicky. So most people don't use it, which is great. So the parts we're using as a TMDS encoder that just transfer the digital data into the same thing that the HDMI use, and the LCD is way more happy with this. So the video DAC we use, because the data I'm outputting from VICKY2 is a 24-bit RGB color palette, if you will. It's always full color. But it's multiplexed, so to save some pins. So you have the HSync signals that we referred to it last time, the VSync, the DE means display enable, which is the blanking. And in that specific case, the data has been multiplexed. And in that design, I'm using a DDR way of doing things. So I use, for example, if we're doing a 640 by 480 VGA standard clock, dot clock, that means that the clock getting into the video deck is 25.125. But on the rising edge, I'm going to send the first half of the 24 bits, which is 12 bits. And on the falling edge, I will send the other part. So you see a little bit of graphics here to show that. And the next table next to it is really about what data is being. So basically, I think it's getting the blue information, the green, half of the green on the rising edge, and the other side of the green and the red on the falling edge. Then the DAC just takes care of everything else, and you get your video on screen. So this is one part that we need. This is ultimately where all the pixels will come out. On the other end, you have the SRAM interface. I call VMEM or VRAM or whatever. I mean, back in the day, VRAM was more dynamic, a specific dynamic RAM, but today is more like a generic term. In our case, it's generic term. I use SRAM, and the limitation of SRAM is really the fastest SRAM you can get. I mean, that is still reasonably priced, and if it's not synchronous, it's 100 megahertz. And the deal for me has been to widen the bus to get more bandwidth out of it. The reason I'm using SRAM, even if it's back in the day, SRAM was costing a fortune and people were using DRAM, which made more sense. And even today, DRAM is less expensive than SRAM. But the reason I kept using SRAM, and it's not because I didn't try to use DRAM, is that ultimately the SRAM is a random access. I can do pretty much, I give an address, I give a read or write, and I can actually have my stuff within 10 nanoseconds, which is still fairly fast. And the difference between VICKY and VICKY2 was because I expanded the bus to 16 to 32 bits, so I could fetch more. So that's the way I went about getting more data out of the memory, to get higher resolution, to get more feature like tiles and bitmap, and so I could have more data being moved around. The reason the SD-RAM is a burst type memory, right? So it's really good at bursting things out. If I had only used it for doing bitmap, then SD-RAM is great because you just burst on a whole line in one shot, and it's really, really fast, and you can go faster than 100 megahertz. But when it came to tiles, for example, or sprites, it's just a small chunk of memory that you go and fetch. So when you're dealing with SRAM, you have like 4, 5, 6, 7, 8 clock cycles before you start doing anything to set up the address, to the RAS, the cache latencies. All these things that you're probably very much aware of are part of the whole transfer. So if you have to transfer 32 pixels, which are basically, in our case, a byte, because everything in that system is 1 byte per pixels with lookup tables. So you would have to transfer 32 bytes, which is 8 32-bit wide, word. So that means that you're going to use 8 bytes, 8 word to set up the whole DRAM, and then you're going to burst for 8. So that means that you divided your bandwidth by 2. So even if you're running 166 megahertz, that means you're still going at 66 megapixels per second, which is just stupid. So there's no way to go around that. So that's why I kind of stuck with the SRAM and decided, okay, if I want to go faster, I just need to put more or a wider. The memory can be less dense, but having a wider bus. And VICKY3, that's what I did. I ultimately have 2 of these configuration. The interface is very simple. There's no DRAM controller. There's no refresh controller. That's also part of the deal. And I just made the calculation last year and say, okay, I can put a little bit cheaper DRAM, but then the overhead to get it to work, the time, the whole thing is not worth it. It's just going to cost me a fortune in time and implementation and make it work properly. So I stuck with the SRAM. So ultimately, there's just a 32-bit RAM, 32-bit bus address. There's a 20-bit bus address data, and the control signals, the byte enables, the output enable, which is basically a read strobe and a write strobe. And if I play my card right, I can pull a 400 megabytes or 400 megapixels per second in throughput with that controller. So All right, so this is what it's outside. I'm not putting it, I didn't talk, or didn't make a slide about what's been connected to it, because so far VICKY 2 has been implemented with a 68,000, a 68040, 65816. So you can pretty much put anything in the front end because, well, from what you're going to see here, you're going to understand why. Because the front end of VICKY 2 is basically a bunch of register level that you can map, and you can kind of remold it to fit the different type of interface. Everything else after that is pretty much the same. So we're going to spend a little bit more time here because I think it's really important to understand the different blocks and what they do. So within VICKY 2, there is at the top level, there's the video text engine block, which is really its own thing. So that guy used internal FPGA memory to put all the character information. And there's another block of memory that has the font information, and everything is done internally. So there's no access to the VRAM whatsoever to deal with text mode in black and white, like one color. Ultimately, VICKY 3, I'll expand that. I'll try to use some external memory to put some colors and do some stuff, but we're not there yet. So this is, and the output of this is going into the video output mixers that I will talk about it a little bit later. But this, one of the features of the VICKY 2 chip is allowing you to do overlay, text overlay. And that's the reason why we can do this, because it's so much different, it's so separated from everything else that it's just everything is synced up. So you just feed the text on top of everything else. And if I was using the VMEM to do video text, then it would not be possible because it would be just another layer. Then there's the mouse controller, which is another block that is separated from everything else because it's simply a small block. It's a sprite, literally, but it's not part of the sprite system. It's overlaid on everything else, which is, it's pretty standard in video chips. And then you start having the different register level, the bitmap register level, which is basically telling in the memory where the bitmap starts, well, you don't need to do the size anymore. There's different resolution. I'll talk about that later. The tile map system is 4 layers of tile maps, and you have access to different, you have windows of, you define a map within the VMEM, and you define your blocks of graphics separately. You can have 8 of them. And then you have register to move stuff around, to move a window within the map. Not going to go deeper with this today, but it's how it works. And I have 4 layers of them. Then I have the master control that just decide what is the resolution and everything. Then the sprite, there's 64 sprites by default in the system, but you can mux them to like a lot more. Right now they're 32 bit by 32 pixels by 32 pixels. The tiles is 16 by 16s. And ultimately the sprites are very simple. You enable the sprite, you put your graphics somewhere in VMEM. There's a pointer that says this is where the graphics is. And you just set the priority on what layer it is, and it's going to be displayed. And then part of VICKY 2 as well, there's the VDMA controller, which is the video DMA, which is, you could say it's a blitter, but it's not quite the blitter yet because there's a lot of function the blitter has that the VDMA doesn't do yet. The VICKY 3 will have way more blitter functions than what VICKY 2 does, although I might upgrade VICKY 2 later. I made 2 different DMA system in all the new retro computers I designed, because I wanted to be able to do VDMA on one side, because there's 2 memories, right? There's the system memory, there's the video memory. And so the VDMA can move block around in the video memory without interrupting the processors. And then if at some point you want to transfer your graphic data from system memory or from SD card, whatever, you use the SDMA, you set up the SDMA, you set up the VDMA, and then you get them started. And then they're just going to transfer data in between each other and then transfer it, in the VMEM. The only problem with this is that the 816 so far, you have to stop the processor. You cannot share the bus. You cannot do like a shadow transfer while the CPU. It's not like you can do it like a 68,000 with the Amiga, because Amiga had so much time in between every access that you could do a lot of things. And that's what the Amiga was so powerful, because they're so so many clock cycles that are wasted waiting and processing inside the 68,000 that there was the VDMA or the DMA controller was taking advantage of that. The 816, we cannot do that because it fetches a clock. It uses both phases of the clock and fetches something every clock cycle. So there's no room to do anything. The 68 SEC is kind of like that a little bit because the clocks, the number of clocks needed to do a processing, to process an instruction went from 7 o'clock to 3 o'clock. So there's no room at all either. So there's a trade-off about doing DMA and VDMA at the same time. So that's why I always say transfer your stuff in VDMA because the buffer of VDMA is pretty big, and just move your stuff around instead of trying to just push your stuff in and then push more and push more and push more. So the register level is really where you keep all the information about where things are, what size, where, how you move stuff around, stuff like this. And then within VICKY2, there's the block I call VGE, which is the video graphic engine. And within that engine, there's the master state, the master state machine, which is basically a state machines that just going to check what line we are. If the bitmap is enabled, is the bitmap block is enabled? Yes, okay, go do your thing and go from bitmap, tile map, sprite maps, one after the other to go fetch the data. And that data, each bitmap or each state machines of every of these different types of graphics is because every bitmap is doing a certain thing. The tile map is doing things in a different way to go fetch the data because it's a different type of graphics element. The sprites are the same. You know, all those three things are really different from each other. And then what it does, it starts the state machine of every block one after the other, and then it goes to send some information of the register level. For example, it basically takes the information from the register level, pull it and push it into the memory access manager and said, okay, you need to go fetch one line of bitmap right now, go and get it. And when you get it, go put it in one of the line buffer, and we'll come back to that. And it goes from bitmap, tile map, sprites, and VDMA. And ultimately, all this information that was fetched from the memory is put in all of those line buffers because the way VICKY2 works is really in layers. And after, when it's been computed, it's been all the data has been grabbed because everything has been grabbed one line before it's being displayed. So during the previous line, so for example, if you start at line 1, so you're about to start a new frame, so you're at line 1, so the line prior to this, that process starts and say, okay, we're at line -1, and go fetch the information from line 1 that is upcoming and put all this data in line buffers, which basically is the line memory. So it's a dual port memory. So you write on one side and you read on the other. But there are two different speed, two different processes to you go through to get that data in and out. And then it goes through the lookup tables because it's at that point, it's just an index. You say, okay, I want, pixel is 20, it means that I want the color number 20. And it goes through the lookup table, and then the lookup table spew out some RGB value, and then it's put for that specific pixels on the line, the value you want. And so this is the basic functionality of the layering logic, but then there's the priority level where I'm going to come back to it later. And then ultimately all that information is synced up with all the VSync and the line counters and all these things. And it's, again, there's another priority level where, okay, is it the mouse is the top level, and then there's the overlay level, and then there's the graphic engine level, which includes all those different lines, which is sprite, bitmap, and tiles. So try to memorize that picture. It's really important. So this is how the layering system works. So like I mentioned, there's the sprites have many layers because they can be intertwined between the different, the bitmap. There's a bitmap on the top, there's a bitmap on the bottom. In between, there's 4 layers of tiles. And in between all those layers, there's the sprites. You can put all the sprites in any of these layers. And you have 64 sprites, which means that you could put, sprites 1 to 7 on sprite layer 0. And you could put, sprite 20 to 32 on another layer. But you have to keep in mind that, depending on priorities, and if you want to concatenate or put those sprites together to make bigger sprites, then you have to make them one after the other so they don't overshadow themselves. You have to keep in mind also for the collision system. I'm not talking about the collision system, but there's a collision system, which is not great, but it's there. For example, you would put like your protagonist characters on your sprite layer 1 and you sprite layer 0, and then you would put an antagonist on the other layer for the collision system to work. But I don't want to go too deep into this. But like I was mentioning before, all that data that's been fetched from the memory is written in one of those lines, and one of those lines represent a priority level. So for example, if the sprite layer 0 would be in that line buffer 0, the bitmap would be in the next one, and so on and so forth. So what happens is that when we're ready to go and transfer that pixels offset or pixel pointer to the lookup table, there's a counter that goes through, at the beginning of the line buffer, just go through every pixels and look, okay, which one of these, we read all those values at the same time and say, okay, which one, okay, is there a 0 on top? No. Okay, so this is the pixel we're going to show. The next pixels next to it is like, okay, is there a 0? Because 0 represent transparent. So 0, yes. Okay, the next one, there's 0, yes. Okay, moving on. If you don't come across a pixel along the way, then you end up having the background set color, which is just an RGB value, and that's what you've been displayed. So if you come across a pixel before, then you're going to display that pixel before. So this is how the priority level works in that system. I could have put like it could have been done in different ways, because there's like a Z buffer I could have created or something that could have given each element a different variable, but then you expand on the buffer size and the information you need to. That's what 3D graphics were doing, right? You just give a value of Z, and you compare the value of Z with the other pixels, and you can, remove pixels you don't need. But at the end of the day, one of the challenges was during the design was like, ultimately you need to read all the pixels anyway, because at some point you need to compare them all together. So the idea of line buffer was possibly the best way I could go about it. And considering I had the resources in the FPGA, then this is something I could do fairly easily. So this is how the layering systems works. So after that, this is the state machine in a very simplistic way. The way it works, bitmap in principle is very easy. This is the easiest way to implement. You want to do a graphic system in FPGA, bitmap is the easiest of all, because it's just, you go read the data in the memory and you put it in the buffer somewhere. And when times comes, you just read it out at pixel clock at the right time, and you get your data. It could be 24-bit, could be 8-bit. You could have a lookup table. Obviously, you need to take into account the time it takes to read the data off the lookup table. But without going too much details, it's very simple. It's straightforward. You set an address in VRAM, in our case, and you say, okay, it's buffer at beginning at 0. You say, go read this. So later, I'll show you when it happens. But it's ultimately, the master state machine says, hey, the user wants you to go and have a bitmap image. So you're on, you have an enable signals, and then there's a trigger that says, okay, this is your queue, go fetch the data. So I'm going to fetch all that data at 400 megabytes per second, and I put it in the line buffer, and we're done. And that's the thing, we can enable or disable every of those blocks, but this is very simple. And then the state machine knows where on the image it is, so it can offset the place it needs to go. So if I'm on the 30th lines, it's just going to go fetch the right address at the right time and store in the line buffer. That's all it is. So in that case, the state machine is only the logic or the functioning logic behind it. What happens is really the MAM, which is the memory access manager, is being told, okay, this is the bitmap time. I'm going to give you an address in the memory. I'm going to give you how much data you have to go fetch and latch the data in and say, okay, this is where you need to go. Basically, it's a counter that has been set up and a comparator that's been set up, and you say, okay, go fetch the data, and everything else after that and done, you go back to the state machine, master state machine, say, okay, we're done. And the state machine, what it does, it just moves on to the next block. So before we go into the next block, the different in VICKY 2, you have the borders that you can set up. You have the invisible portion of, it's a virtual place, if you will. It's like not in the memory, it's not in anywhere, it's actually in the blankings. But the starting address of the bitmap is 00, and you have you can have a border, but you can have, usually when you're using the graphic engine, the border is on top of everything. It's like it's a layer for itself. It's like the border is done in the hold on, sorry. The layer has been created into the video output mixer. It's not created in the graphic engine. So it's really an overlay of a color. That's all. And the engine, the VICKY 2 engine can do now, actually it's one is missing. You can do VGA, normal VGA, and I call it double pixel, which is you just make things bigger. So 320 by 240, 800 by 600, and then twice or the division of the two, I guess. There's a new one, which is 640 by 400, that's 70 Hertz, to, have the same as the C64 for the one that likes the big pixels. But all those are at 60 frames per second. And so the bitmap is very, very easy. Moving on, next we have the tile map. The tile map is really tricky because a tile map is like a font, a set, right? It's a text thing. You have in your memory, your main memory, there's an information. In our case, it's a 16-bit information for every tile. Within that information, there's enough set, or there's a tile number. We say, hey, this tile, from this tile set, we created all the graphics, which is a block of graphical data, like a font set, same thing. But I've put a 16-bit, it's in 16-bit because I wanted to have assigned the lookup table. I wanted to have, you can actually assign multiple graphic sets. So it's not only one set you can point to, you can have 8 of them. So you can have like way more tiles. You have 8 sets of tiles that you can use within one set of one map. And then there's the collision system and so on and so forth. So in the state machine, what it needs to do at first is that since the graphic element is 16 by 16, you have to divide your screen by 16 by 16, right? So within, for example, for the first 16 lines of video being displayed, then you have one tile that has been displayed. So when you go fetch the data for the tile, for 16 line, you're going to go fetch the same data. And usually I'm going to go and fetch it once. So at first I'm going to go in the tile map, and the tile map will tell me, the first line of the tile map will tell me what tile you want. So this is done first. And then what I do after, I'm going to access the memory a second time, and I'm going to go get the graphic in small chunks of 16 pixels and all the different tiles, the tile blocks, graphic blocks, to go get the data I need to display. And that information will be put into the line buffer for each layers of tiles. So if you have 4 layers enabled, I have to do that 4 times. And then when I'm done, I'm done. This is what I have to do. So in a way, it's a lot of back and forth and go fetch it. So after I'm done with the first 16 lines, then before I get into the 17th lines, I need to go get the new line of the characters or the tile map information, so I can know which graphics to display in the next 16 lines to follow. So definitely a trickier logic to do tiles. So how it's presents itself is like in the memory, you're going to set up a tile map. The map is where your tile information is. And the tile map can be really big, and which saves a lot of time to, instead of pushing data in and on each sides and everything, to make it, if you want to do scrollings and not RPGs, but platformers and stuff like this. The way I saw it, the way I implemented it was really, you set up in your VMM the tile map, the sizes, and you put all your information in there. And then you set up, there's another configuration that you say, okay, the window of the screen will be at X and Y position in your tile map. And so you're moving, you just need to move your window. Your graphics don't have to move. You just have to move your windows into the tile map to get your stuff. The only thing it doesn't do is the wrap up when you go back, but you can cheat and put stuff on the side, on the right side for the left side to repeat. And then you move your window back to where it was before, right? So there's tricks you can do. One of the reason I put so much memory at the time was that back in the day, memory was a big limitation for graphic engines and everything. So they put a lot of tricks in the hardware engine to do a lot of stuff like inverting, vertical inversion, horizontal inversion. I mean, the SNES, all these consoles had a lot of hardware tricks up their sleeve to really reduce down the amount of memory needed. So you would have wraparounds and stuff like that automatically inserted into the engine to do this. It becomes very complex to put that in place. It complexifies the design a lot. So the one way to mitigate that is to put more memory so you don't have to do it. So now memory is kind of cheaper than it used to be, although nowadays the memory has increased dramatically. But let's say that I can get that memory for cheap. It's still a very economical good way to do it, because I don't have to spend months on end, because I'm only one person in the end. These guys were like 20 Japanese engineers working full time for months on ends to design these graphic engines. So I don't have that luxury to spend 3 years to develop just a wraparound logic to make it cool and fancy. So memory, I have plenty of memory, so expand, use the memory, and usually it does the trick. So in a way, the tile system is pretty powerful in a way, because you have this capacity to have like 4 different layers, and you don't have to do much aside of just putting the graphics, moving things around. Still, the graphic engine does a lot of work. The resolutions are the same, obviously, one resolution for all those features to be displayed at the same time. Another aspect of the tile system that is important is that you need to account for a border for the scrolling system, for the smooth scrolling system, because it does a smooth scrolling automatically. So you need to account for an extra line and extra sides on each side. So when you're moving around, you have data to cover those scrolling areas. So for those who plan on using that chip, then you have to keep that in mind. It's one of those things that people don't get right away. So moving on. Finally, the sprites. The sprites are another interesting aspect. They have something very specific to them, because sprites are just little blocks of data that you can display anywhere on the screen, right? So it's not a full width of the screen. Like bitmap, tile maps are always very precisely, exactly. You need to go fetch the data for the whole line altogether. The sprite is not that at all. It's just a small blocks of 32 pixels every line. So the state machine needs to track the first of all, you need to enable it. It needs to be enabled. You need to go through the 64 sprites. You need to identify where on the vertical level they are. So are you basically the same machines go through every sprites and say, hey, are you enabled? Yes, no. Are you presently visible? Are you needed on that line? And yes or no. And if you are, then you need to go fetch that data in the VMem. And then what the state machine does is takes those 32 pixels and put it exactly on the line, the buffer line, where it needs to be in relationship to the rest of the display. So if it's on the 30, like it's the X coordinate of the sprite needs to be 32 pixels off the sides. So you put it in the right space. The sprites are tricky because of the line system. It requires me to erase the line every time. So I need to filling the lines and putting new sprites information, clearing the lines, which is not the case with the others because I fill the lines every time. And then I go through priority. So if I go through sprites and then I have one, let's say I have a sprite that has been displayed at the coordinate X20, but I have another one at at coordinate 25. So I need to go over the other one. So that's why I need to start from the lowest priority to the biggest priority. So I don't have to worry about, oh, this one is more priority. I need to keep the data for this one. And because also the data in the VMem for the sprite is at 32-bit boundaries. When I start putting in the screen, it's a byte boundary. So I need to deal with this. So I have to put the information into a temporary buffer because I read it in words, but I'm going to write it in bytes. So I need to put in a temporary buffer, and then I can put it at odd addresses and stuff like this, which is another weird things, but yeah. And then I go through all of them. And yeah, and I have to also look a line prior to it. So I need to identify, okay, are you a sprite that's going to be displayed the next line following, and so on and so forth. So same thing, but the sprites are really tricky in that sense with that kind of system. And in the case of the sprites, when you have a sprite, if you start a sprite outside the screen, so the X and Y's are at 0, 0 when you're totally off the screen. I'm not talking about the border. I'm saying really out of the screen. So to get it to display on screen, you would have 32 by 32 to see it at the corner. The sprite information also going to expand as well. It's going to double up. All these things when you're in double pixel mode double up. And yeah, so this is sprites in there. To conjure up a sprite on screen, it's in terms of logic implementation, it's pretty tricky for the system I have implemented. But otherwise, it's pretty simple. It's on and off. You just assign the lookup table, the coordinates, and you say where it is in the memory. That's very simple. And finally, okay, so this is the big chunk before we're done. Where things happen and how things happen, it's really during the video, with the video portion of this thing. So when the video starts, you have a very long blanking period. And this is where, because the access to the VRAM is limited. You cannot there's only so much you can do with VRAM for a certain amount of time. So during the V-blanking time is really the time, if you have any VRAM VDMA to perform, this is where a good portion of it will happen. After that, it's just very leftover time from the line. So like I was mentioning, the way it works is that I put the line a little bit, farther away from the beginning, but it's the same principle, it's the same concept. Is when there's a line being displayed, during that time, the information for the next line is being fetched from memory. But before the line is being displayed, it's actually the transform to, if you remember, there was a lookup to the final RGB line. This is where the process of transferring and prioritize the pixel is being done at the horizontal blanking period. So before the line starts, well, while or at the beginning of the VH blanking, the processes of going through all the pixels and to see which one is which and which one will be displayed is being done. And then it's been stored into the final RGB line. So we have the information to be displayed. We don't need the VRAM anymore for that active line to be displayed, about to be. Okay, it's been displayed now. So meanwhile, the VMEM is available. There's nothing to do. If you don't have any graphics, then the VRAM doesn't do anything. But let's say, for example, you have a very complex game. You want to have a background with bitmap and stuff and blah, blah, blah. So how it goes is the master state machine will say, okay, bitmap, do we need bitmap? So that section can be there or not, but it's fixed. We know how much time it takes. It's going to take a portion of the bandwidth of the memory. And so, okay, go fetch the information we need for the next frame or next line. And then it goes, okay, we're done. Go get the tile. Tile is semi-fixed because we know how much time it takes to go get 4 layers. So, but it could be a short 1 layer, 2 layers, 3 layer, 4 layers. So we just took a portion of the bandwidth of the memory to go get that. And then there's the sprites, and their sprites is very variable depending on how many sprites. But keep in mind that if you can go fetch 32 sprites, but you're gonna only see 20 of them. It doesn't matter. You take the bandwidth anyway because you had to read all this information. And I wish I would be able to predict which one will be displayed before and after, but again, it complexifies everything. But so that period is very variable. And ultimately what left over is taken by, you can use it to do a little bit of transfer will be happening, but usually it's not much, but throughout the rest of the image, you can, steal a bunch of time to go continue UV transfer. So you have to keep that in mind. So if you're transferring new information for that frame to come, then you might have some shearing in the screen, stuff like this. It's the same thing with the sprites. You have to be careful to make sure the sprite is completely finished before you start moving it around, because then you'll start seeing some shearing or half a sprite displaying if you want to do muxing. But one could actually use that to its advantage to start doing some weird effects. So there's definitely a lot of room you can change everything about the sprites during the display of the image. So the good side is that you can take advantage of it. The bad side is if you don't do it at the right time, you could have some shearing and half a sprite there and half a sprite there and so on and so forth. And yeah, that's it. So that time is, so if you enable everything, you won't have any leftover stuff. And that's one of the reasons it's kind of difficult to put more sprites in, because I don't know how much time do I have. So if I knew that, well, I could do it. If I knew that the tile map is not available, I could increase the number of sprites to 96. If I know that the bitmap is not there, I could increase the number of sprites because I have more bandwidth to give to doing sprites. But then, so yeah, so that's basically it. This is how the time is being shared, and that's the limitation of the controller. So how much bandwidth you have to go fetch that data. And VICKY 3 might be different for that because I have 2 buffers. So I can ultimately go fetch that information on both buffer at the same time. So I can reduce by half. So I can go fetch way more. But we'll see about that. So where are we? So that's it. So this is, I don't know, this is really like in the mouth. It's like a lot of information. But in a nutshell, this is how the whole concept works. This is how this is really the functionality of how I thought about it. And again, there's many, many ways we can go about designing a controller. I'm not a, seasoned 3D graphic person that did custom chips with 4 ATI, stuff like this. I really just created this from nothing. But at the time, that's what made sense. And it still makes sense today for this type of things I wanted to do. So that's it. I don't know if you have any questions or, yeah, I'm
can
done.
Hear me?
Yes.
So there is one person had said something in the YouTube chat. So I'll ask that question first. It was earlier on. It says, how does this SRAM and VICKY 2 bus speed compare to Mac 2 or Mac 2 FX video performance?
Mac
Macintosh. So the Apple Macintosh 2 and Apple Macintosh 2FX.
I'm not sure. I'm not very familiar with the Mac 2. I know that the Mac early on was sharing the memory to do graphics. So, and I think it was doing what the Amiga was doing, was stealing the CPU cycles to do access to it. That be my take. Is it better? I would say yes to a certain degree, and I would say no to another. The problem with that structure or the way it is implemented is that it's very fast. It's very fast to do a lot of graphical element at the same time. The biggest problem is once you want to read data off the VRAM, which is very, very limited. So when I talked about, for example, the I think the graphic at the end shows it better. So this time, okay, this VRAM time, this VDMA time is really where you can pull data off the video memory. And it's very limited. So because there's 2 types of transfer, you can go fetch one, because it can be useful to fetch data out of the graphic engine for collision systems. You want to know what pixels is for that bitmap and you want to compare it to whatever happens. And so it's tricky because either you're going to go, the way it works right now is that you push a request into the VICKY and you say, I want to go read the pixels. And then within the state machine, the master state machine, it says there's a portion I forgot to put, but there's a FIFO. And when there's time, it's going to go fetch that pixel, put it in FIFO and say to the system, hey, your pixel you wanted is there, right? Or you can do a transfer of VDMA to SDMA to a block of data that you have in your VRAM. But then if you don't have enough time, you might not have all the blocks you need. So it's tricky to read because everything goes so fast. There's really no time dedicated to that. In the old system, for example, with the C64, you could share the clock in 2, and one time is the CPU, the other time is the video memory. So you can share, and it's easy, it's because you have that time. The 816, for example, I said it, they use both sides of the clock. So there's no time for me to use that time, nothing happens, to go and fetch the data. So I think back in the day, the system was still pretty slow and the CPU was taking still a lot of time to do a lot of things to go and split that time where there was nothing happening. You could steal the bus, go read the data off, and give it to the CPU or to write something from the CPU, so on and so forth. And as far as how they fetch the data off the DRAM, it's probably the same way. So they probably put in a buffer or a line buffer, and they just went and displayed because they didn't have all the colors and stuff like this. But I think after, I don't know when exactly it happens, but the video cards brought this idea of separated buffer, so you could do all your things. I mean, I wouldn't see an RTX 3080 using the main memory to do all its tricks and stuff. So I would not be able to answer specifically, oh yes, it's so much better. But if I remember, the Mac at that time were not colors. They didn't have all these different graphic features, because if I was just doing bitmaps, I would be way, way better. But again, hopefully I answer some aspect of the question in a way.
Okay. Someone else is asking for a demo, but I don't think you have that readily available. Asking for a demo of like the video processing or something like that.
A video, an example. I have people who design games and stuff.
So maybe you can later supply in the Discord some examples of that.
Oh yeah, I can put some links. They can go on the website. The first thing on the main page is different videos of people who design games and stuff. I mean, it's pretty cool. Hold on a minute. I think I have some links here. I'll give it to you on the Discord. But keep going. I'll answer the questions.
The next question is, how big is the LUT?
The LUT is, the lookup table is, it's a lookup table from 8-bit per pixel. So it's a byte to a RGB, so a 32-bit, because the dual port memory and FPGAs are, 2 exponent something. Right now, there's no transparency. So it's RGB 24-bit. So that's why you can, out of 256 combination, have a full RGB palette. The way it is done is that you can choose 8 different palettes. So ultimately, in one screen, you could have 2048 colors, 8 times 256. That's it, right? It's yeah. Yeah,
sounds all right
2K, 2K colors. So you could have 2000 variation of the full color palette. That's it. So 2,248 out of 24 million, 16 million colors. And you can pick and choose which one you want.
All right, let me take a question from the live audience, and then I'll just alternate back and forth. Anybody here in person? I have a question. Oh, he was looking for a demo too. So, all right. So when you get the link, that's fine.
I just posted on Discord. So there's this. This is one. This is a great one.
And all right. So I'll read the next one. I read something about a hardware line acceleration. Is this true? And do you intend to add other kinds of graphics accelerations?
Okay, in VICKY 3, I want to do a line acceleration. I want to implement a line acceleration algorithm in there, hardware, a very simple one, nothing too complex. So yes to that question, that's definitely in the wish list, because that's the thing. I'm on the verge, the release of the A2560K, which is the keyboard version that I've announced last year at VCF, and the Gen X is about to come out too, finally. So this is really the base to implement VICKY 3, which has 2 different buffers. So I'm kind of definitely more room to implement these things. So the line algorithm is definitely in the wish list and will be done at some point when I'm, shipping stuff and I have my parts to ship. Other elements, I definitely want to get the collision system to be way better than it is now. It's difficult to say because I try to go and implement stuff that people need at this point. Because there's, you can go on a tangent and try to design everything you want. And then you come to a point where, okay, you know what? I think I need to stop. because it's just people don't use it, right? It's just a waste of time to develop stuff that people don't use till they decide, oh, it'd be great if I had that. So maybe more sprites. Something I wanted to do was maybe have different sizes of sprites, maybe more of them. The line algorithm, transparency support, and collision system that is definitely better. And obviously the VDMA having more, blitter type system type features. So in the short terms, that's what I see. I don't, maybe because I'm also trying to tackle, because the community brought a lot of people. At first I want to attract, by doing this, I wanted to attract a lot of people to do games, but games need like an audience. And I attracted more people towards like GUI and OSs and stuff like this. So these require stuff that are not necessary on the other side. So I'd like to maybe brought more feature to support like a GUI environment type of things. So that's the kind of thing I'd like to do to support those endeavors. So it's really at this point in time, I'm really trying to bring stuff that might alleviate some of the challenges that people wanting to do a GUI environment and stuff like this would have to go through. So.
Okay. Next question. Will VICKY 3 be backward compatible with VICKY 2 code?
Yes.
That's good. That's easy.
No.
Good.
Yes, it needs to
happy.
be.
Yeah,
it needs to be. I'll put more registered on the side and not map at different places. But yes, it needs to be. Yes.
All right. Next one. If the line buffer has 8 RGB, is there alpha blending?
Well, that's what I was saying. The alpha blending is there. The transparency is a bit tricky in that structure, in that way of doing things, but I'd like to put in there. Like I said, early on, there was a lot of desires for a lot of things, but what happens is that there's a lot of desire for a lot of things at some point, but nobody does anything with them. When it's like, oh, if I have that, I might buy a machine, or if I have this, I might do this, and they never do. So it's kind of, I'm not saying it's sad, but for my own desire, for my own edification, yes, I would like to do a transparency, implement transparency in VICKY 3, yes, but I will do out of my own desire. Or I would do it out of, oh, I'm doing this game, I need transparency, absolutely, can you do it? And I would say, okay, you need it, so we'll try to implement it. It's like this fine line between, I'd like to, because it's part of the philosophy, to really get in there, do some work, learn new things, and struggle a little bit, because the mother of creativity is really the struggle, and try to pull it off if you don't have everything, as opposed to give them everything and they don't do anything with it, because that's what's been happening for the last 20, 30 years. We've been having everything, and we've been like, we have tons of memory, we don't care anymore, and there's like gigabyte size software that you're like, what's going on with these people? I was about to swear. What's wrong with these people? They're lazy, so it's a platform to stop being lazy. So yes, I want to enable people by giving them certain feature that would make their game better, but we're not at the point where people are, oh, I have this great game, it's going to be so much better if I add this. So it's kind of a vicious circle of me wanting to get them in, but if I spend months on it to develop a feature that nobody ever used, what's the point, right? I have sound chips that they're incredible. They're all together on one platform. Nobody uses them. So what's the lesson to be learned from that? And people go crazy for the X16 with a beeper. It's like what the? So it's the same thing. So if people ask, I will create it. But but they need to get involved in the machine first. It's not like, oh, if you have this, I'll buy one. No. Get one, get involved, and then we get there. I'll give you what you need. It's more like this. Thank you very much for people for coming live, and everybody who's are virtual. Thank you for VCF for inviting me again. Thank you, Jeffrey. I know you're working very hard. It's your baby. Thank you for inviting me again. If I can do anything for you, let me know. And I guess I will see you tomorrow.